Hi everyone, welcome to this new video lecture of fluid mechanics. In this lecture, we'll discuss the pressure measuring devices, single column manometer. Actually, in the previous lecture, we have started this topic of pressure measuring devices, and we have seen that for pressure measuring devices, you have several equipments are there, and as I already discussed, one is manometer, another one is mechanical equipments are there, mechanical gauges are there, and in the manometer, it was categorized into three types. First, initially, it is two types. One is simple manometer, another one is differential manometer. And simple manometer is again, it is categorized into three types. One is piezometer, another one is U-tube manometer, and the third one is single column manometer. So in the previous lecture, we have discussed regarding the piezometer and U-tube manometer. You can watch that video. And now we'll discuss about the single column manometer. Actually, the single column manometer it is a modified version of U-tube manometer. And why we are calling it a modified version of U-tube manometer? If you have seen the previous video, you can see the U-tube manometer is having a U type of shape of tube is there, and the area is both the tubes are similar, right side and left side. However, this single column manometer, there is a difference is there. You can see one reservoir is there here. This is the reservoir part, and this area of this reservoir is actually 100 times more than the this tube manometer. Okay, so that means you can say the larger content area of this reservoir, which actually we is to consider 100 times more than the this right side tube manometer. Okay, and that's why if any kind of differences in this pressure in the reservoir will be there, so that can be neglected. It's very small will be there, but however in this right side we will get a huge height difference than the previous one, because it is very small compared to the area of this reservoir. So let's discuss about this single column manometer. It is actually categorized into two types. One is vertical single column manometer. First one is vertical single column manometer, and the second one is inclined. Second one is inclined single column manometer. So let's discuss first one, this vertical single column manometer. So this is the diagram of this vertical single column manometer. Here, now this is the pipe is there. Okay, so this is the pipe through which the water is flowing, and this is the, you can see this is the pipe through which water is flowing, and the point A where we need to calculate or where we need to identify the pressure at this A point. Okay, now before this actually how the structure is to there, let me slow one small diagram, let me draw you. So this is the here, if we consider like this, so yeah, so this is the structure of this vertical manometer is there. Okay, so in this tube, in this pipe, you can see there is a fluid is there, which is suppose little water. So water is flowing inside this pipe, and we need to find out the pressure for this pipe. Okay, and here we are having a heavy liquid is there, that is this is the heavy liquid, that is nothing but mercury is there. Okay, that is mercury. Suppose this is the level of, you can say from here you can say, let's start, this is the heavy liquid is there. Okay, and now this is having a layer of up to this. Okay, let's start from here. So this is the heavy liquid which is present in this container. Now when the liquid is flowing, or when the fluid is flowing inside this pipe, okay, so this liquid will give a pressure to this. When, as I told you previously also, let's fix a valve here, and when you open this valve, Okay, when you open this valve, then there is a flow of liquid, inside this tube. Okay, now this is the lighter liquid. Let's consider this is the lighter liquid which is present here, and when you open this valve, this liquid will be give a pressure on this heavy liquid. Okay, so initially suppose this is the separation line is there. Okay, now this one we can consider, this is suppose x-axis is there. Okay, this line is suppose x-axis there. Now when the liquid will give a pressure on this surface, on this heavy liquid, then this difference of layer, you can say, is very small will be there, because this space or cross-sectional area of this container or this reservoir is so large that this change in or difference in height will be negligible. So that difference of height we can consider, that is delta H. Okay, but due to this small change in this larger reservoir will be give a big impact on this right limb side or right container side, so that this falling in the fall in or you can say increase in this liquid of light liquid from XX to, you can say, another one YY, because see, this is the gap is there, that gap is actually delta H, as I told you. And after this giving a pressure on this heavy liquid, the heavy liquid will be fall from XX to YY, which is delta H, and this delta H is going to rise in this other side, on the right hand side. So how much increment will be there? So initially it was up to in this layer suppose, up to suppose XX layer was there, and now up to XX layer, then now it is going to increase up to a height of H2, because we know that this cross sectional area is very large, and what about this tube cross sectional area? It is very small. So definitely if it is a very small change in there in this, but you can identify here a huge difference in the right side, because the area of this tube is very small. Okay, even you can observe these things in a container, like suppose in our home we know that we are having a water tank, and there is small change in water level in this tank, that can be give a 3 liter of cold drinks bottle fill. Suppose if you want to measure the water level changes in this tank, okay, you cannot identify that much changes either, because it is a huge container, like 1,000 liter containers are there. But same, if you take difference in that container is very small, but if you measure the same amount of water or same volume of water in a cold drinks bottle, that will be give you a huge big difference, or you can say a height increment will be there, which is measurable, or which you can say it is a noticeable height. Anyway, so this is the logic of this single column manometer, vertical single column manometer. Let's see so how to identify the pressure of this A point. Okay, now here what are the things are there? H1. So H1 is the nothing but height of this liquid, height of this light liquid from the center point to this XX point. Okay, XX line. And now H2 is a what? H2 is the liquid increment, or you can say the liquid increase in the right side limb after giving a pressure on this. So how much increment was there in this side? Okay, so that is the heavy liquid height of heavy liquid in the right side. Okay, and delta H is nothing but the change in liquid region, or change in, or you can say fall of heavy liquid. Okay, this is because initially up to from this XX line, after that YY came, so there is a fall of this heavy liquid in this reservoir, that is delta H. And similarly rho 1 we can consider the density of this lighter liquid, and similarly specific gravity of this lighter liquid, and similarly density of this heavy liquid and specific gravity of heavy liquid, and area. A is the cross sectional area of the reservoir. Okay, area is the A equal to reservoir area, cross sectional area, and small a equal to the cross sectional area of the tube, the right side tube. Okay, and PA is the pressure at this A point need to be measured. Okay, so these are the terms which included here. So let's find out what are the things will be need to identify it. So first things we need to identify actually what is the pressure level at this right side, okay, above the datum line. Let's see the datum line is YY is the datum line here, okay. This is the YY datum line. Let's find out first the right side. Okay, right side is easy one. Only one liquid is there, so we can find out the pressure above the YY datum line. The pressure above the YY datum line. Okay, that equal to, we know the formula, rho g h. So h is nothing but there h2 is there plus this delta h. So that is nothing but we can write h2 plus delta h. So this is the pressure above the YY datum line, this side, right side. And similarly here we can write the pressure above the YY datum line. We can write, first thing is here one more pressure is there, that is our pipe pressure. So that is PA plus the pressure from here, from this YY2 to the center point of this. So that one we can write, you know, this is, we can give rho 2, okay. This one rho 1, we can write G, and here also similarly H1 plus delta H. So this is the value at this right side, left side, and this is right side. So now we can equalize these two pressure equation, right side equation and left side equation. So what we'll get here, let's write down this PA plus rho G H1 plus delta H, okay, equal to what we'll get here, rho 2 G H2 delta H. Okay, this is pressure at the right side, this is left side, and this is the pressure at the right side, and this is left side. Now if you solve this, let's write down here, let's keep the pressure A one side and remaining term other side, rho 2G delta H plus H2. Now that side term will come other side, so rho 1G, we can write rho 1G, you can write rho 1G, here bracket start, you can write H1 plus delta H, okay. Now here delta H can be taken common, and we can write PA equal to delta H, and here we can write, what is that, rho G, this minus will come, okay, that is rho 1G. If you solve this, then we can get it this one, like rho 1G delta H minus and rho 2G delta H, that is plus. So delta H take common for this, rho 2G minus rho 1G, okay. Now here we will get rho G H2 plus rho G H2 minus this one, rho 1G H1, okay. Now what is the value of this delta H actually? So delta is actually nothing but this is the fall of heavy liquid in the reservoir. So delta H, what we can write, so delta H is nothing but we can write, this is actually the fall of heavy liquid. So we can write the fall of heavy liquid in the reservoir of the which side, left side, that equal to the rise of liquid in the right side, okay. You can see here. So how much fall is here happened, that is nothing but delta H. Due to this, how much rise of liquid in the right side, that already have discussed. So we can write this delta H equal to this area into H2, okay, because we can this equation actually from where we'll get that volume, okay. So what is the volume of this? Let's suppose we can write A is the reservoir area into delta H, that is the fall of heavy liquid, equal to again this side volume, this volume and that side volume. That side volume is again area into height is there h2. So that one we can write delta H equal to small a by capital A into h2. So this is the delta H value. So now delta H value we can keep it here in this equation. Okay, let's keep it the delta X equation, that is nothing but A by A into H2 and bracket start rho 2g minus rho 1g plus rho 2g H2 minus rho 1g H1. We can see this area by area, A small a by capital A, as I told you already previously that the container, this reservoir area is 100 times larger than the this area of this tube small a. So this value will become very small, because suppose it is 100 times more than this, means this is the 1 meter square, means this is 100 meter square. So the value of this total part can be negligible. So because it is due to very small. So finally what we can write, the pressure at A point is equal to nothing but rho 2g H2 minus rho 1g H1. So this is the final pressure equation for this vertical single column manometer. Okay. Similarly, another one is there. This is inclined one. Second type is that I told, that is inclined. In the inclined also similar kind of thing will be there, nothing different. Only on behalf of this vertical right side column, you will get inclined here. Okay. And that inclination is nothing but how much angle inclination? That is the angle of theta. Inclination as an angle of theta. Initially it was, it is like that, and now it is changed to this one. So this, see, already here also it is drawn. Initially the height was h height was there. Now it is with an angle of incline, and that to be length is given L. So if you want to, put the value of h2, or you can say the value of h2 in terms of L, if you want to calculate, then we can write here, okay, because same, remaining all the things are same, only here on behalf of this vertical column, here inclined column is there. That's why this is inclined single column manometer. Only the difference will be here, the H2, initially H2 height was there. On behalf of that, we can write this one in terms of vertical direction. Okay, this is horizontal direction. If you want to write this L in terms of H2 in this vertical direction in terms of theta angle here, so that one I can write H2 equal to L sine theta. L sine theta. So what is the previous equation what we got? The same thing we can write PA equal to, what equation we got here previously, rho 2 GH2. So same thing we can write rho 2 GH2 minus rho 1 GH1. Rho 1 GH1. So immediately we can put the value of this L sine theta. So that is nothing but rho 2 G L sine theta minus rho 1 G H1. This is the again pressure at A point. Okay, I hope you understand how to identify this pressure at different single column manometer, whether it is inclined or vertical. Both are same, only the difference is theta angle here. So if you are having any doubt regarding this single column manometer, vertical and inclined, you can give a comment on the comment box. Thank you all.